has been a partner with Mentor Graphics for over 16 years, and we are happy to continue to be a partner with Siemens, and Siemens just acquired Mentor Graphics about a year ago, so it's still in the infancy process of going on to joining in with Siemens. So we cover a lot of different products for Mentor Graphics, from mechanical tools to EDA, even to some IC and FPGA tools. So really any of your needs that in the electronic design automation space, we'll be able to help you out with that. So our territory, as you can see here highlighted on this map, is basically the Midwest and the West Coast, not including California, for the United States. We might also have some customers in the eastern side of the United States, and their distributor for that territory is TriLogic. So if you're not familiar with your sales rep there, you can definitely get into contact with me, and I can find out who you should be in contact with for more product info or pricing or anything like that. We do have a lot. Oasis Sales hosts a lot of webinars. We try and do at least a few a month. So you'll see down at the bottom we have oasissales.com. That's our website. If you'd like to go check out a few of our other webinars that we've hosted, they're all on YouTube, so you can go ahead and view the archive version of those. Before we get too started into this, I would like to just say to save the date for our next Did You Know series, which will be focusing on expedition routing automation is your productivity breakthrough. So this will be hosted in about a month from now, same time on February 15th. And we'll be sending out an email after this just with some more information on what we cover today as well. Thank you about that. I'm sorry I was not showing my slides there. Sorry about that, but thank you for letting me know. Just to cruise back here a little bit, this is our current territory. We are on the Midwest side of the United States, and then TriLogic will be on the East Coast. So that's who your sales rep are. And then, like I said, oasissales.com, if you'd like to check out a few more of our archive webinars. We cover a lot of things from simulation to schematic capture to actual PCB layout and manufacturing output. So we try and host a variety of content, so hopefully anything on there will be able to fit your needs. Okay, and then our next webinar on expedition routing automation will be on February 15th, 9:30 Pacific time. So if that sounds interesting, we'll be sending out some more info on that, and then you can also save the date on your own calendar. Okay, and then this will also point to our YouTube channel. You'll see we have webinars here, both in the pads, expedition, HyperLynx flow. So anything that you're looking for that we can help out with, you can find either on our website or on our YouTube channel as well. So we are available to come to your office and maybe have a general session Q&A, or maybe delve down into a demo of some sort, or help you out with your current installation base. I myself am one of our technical representatives. You'll see my contact information there if you'd like to maybe grab a quick screenshot or write that down. I will show this again at the end of the presentation, so don't be too concerned if you don't get it right now. But again, my name is Kyle Lake. I'm an application engineer that focuses on the board system division for Mentor Graphics, including Expedition, PCB, Pads Professional, and then HyperLynx as well. Okay, so if you guys do have questions, I have everyone muted currently just to cut down on any extraneous noise or anything like that. But there is a chat box that some of you have already realized, so thanks again for telling me that I wasn't showing my screen, and I apologize for that. But if you have any questions, just ask those in the chat box, and I'll get to those if they're relevant to the time being, or I might wait to the end to address those. Okay, so now let's go ahead and move into actually our featured content here. Again, this is Did You Know You Can Efficiently Screen for SI, TI, and EMI Issues. So just a general overview of what Oasis and Mentor Graphics can provide for you in your electronics designs. So for actual schematic capture and board layout, we have Expedition PCB, which is our enterprise PCB design offering. It offers a lot of high-end routing and design capture capability, as well as a lot of data management wraparounds that can really help your enterprise system complete your designs very quickly. Okay. On the smaller end of the side for the design teams is our PADS, which is more of a desktop-based solution that allows you to do some designs, both complex and simple, very quickly. So PADS can excel in the space where if you don't need a lot of enterprise-level data management or collaboration capabilities, PADS still has the horsepower to get a lot of your complex designs done quickly and correctly. HyperLynx, which we're going to be focusing on mostly today, is for a PCB analysis and verification. So that's kind of a broad term, and there's a lot of different things that HyperLynx can do, from power integrity issues to DDR memory timing to general board level signal integrity checks, even to some EMI and EMC graphical checks. Okay, so we'll cover that a little bit more today. Hopefully most of you are at least familiar with the HyperLynx name, possibly even use it today, so we'll delve down a little bit more into there. And then the last major offering that we do in the board design area is Valor. And what Valor is, it's a PCB assembly, test, and manufacturing checker. A lot of board houses around use Valor just to make sure that their boards are manufacturable and assemblable before actually going ahead and creating those. Okay, so just a little bit to show kind of the current trend with printed circuit board systems. So on the right-hand side, we'll see that this graph is essentially showing the red highlighted line is the average leads per square inch is drastically increasing over the last 2 decades. And what this really means is boards are getting denser, there's more components on the board, there's more routing going from different components to components, which can really lead to having some EMI, PI, and SI issues. Okay, so this trend probably isn't going to be stopping anytime soon. We're always being asked to add more and more functionality to our printed circuit board designs, and that can cause some major issues. On the left, you'll actually see that's one of our Technology Leadership Award winning designs that was done in the PADS desktop PCB design. So that was done in there, and you'll see it's a very high pin count FPGA that's being used right there in the center, and how HyperLynx can come in and help address some of those issues that can lead to. So just some general high-speed PCB design issues. I'm assuming most of you might be currently aware of some signal integrity issues, possibly using rules of thumb just to make sure that you're not coming close to any signal integrity issues. But some general reasons that they happen is timing, crosstalk, and signal quality in just general interfaces. Kenneth, I see that what are PI and SI acronyms? So good question. I'm sorry I didn't address that. So SI stands for signal integrity, and then PI stands for power integrity. Okay, so signal integrity essentially is how the signal looks when it's propagating through your interconnects and through your printed circuit board. So this can be a very important issue just to ensure that all of your signals look clean and they're actually going to be what you expect them to be when they are at the receiver end of your interconnect. Okay. So signal integrity issues that we have just in general interfaces, such as just any transmission line going across your board, is timing, such as the timing of it takes to get through and propagate through that interconnect, and to see if that's going to be too far of a delay. Crosstalk, where the actual you have unwanted effects on traces that are running close to each other. You'll have unwanted effects on one another if those signals are running too fast or they're too close to each other on the board. And then signal quality, just the overall general signal quality going through the interconnects into the board. Even things such as vias can have a major effect on the signal quality seen at the receiver end. If any of you are doing DDR designs, double data rate memory, you know that there are quite a lot of concerns that are associated with that, such as full time enclosure, slew rate derating, and write leveling. That is in some newer technology that you can do some write leveling. HyperLynx offers a HyperLynx DDR wizard, which I unfortunately won't be covering today. It's just, we do have a webinar on our website that goes into great detail about the DDR wizard. If that sounds interesting to you, I really urge you to check that out. But the DDR wizard essentially can go in and verify your interconnect and your design to JEDEC standards for timing. So just to make sure that those are going to work on your first spin of the board. And then SerDes, we have loss, impedance discontinuities, and bit error rate prediction. So you can see on the right-hand side of the screen, we've got an I mask and an I diagram, and that's mostly going to be used for SerDes or channel design. HyperLynx can handle all of that as well. So power integrity, we can definitely have some issues with our power integrity. And our power distribution network can be affected by a couple of different things, such as neck downs, a lot of vias kind of creating many holes in our plane, which can really affect how much current can get through that plane. So some things that we have to be concerned about in the DC realm or very slow speeds is voltage drop and high current density. So I'll be showing today how HyperLynx PI, power integrity, can really quickly and effectively check your power planes, your power distribution network for voltage drop and high current density. Also in the HyperLynx power integrity realm, we have the ability to check your power planes for in the AC realm. Essentially, this is going to be looking at the impedance profile of your power planes to make sure that we have a nice, quiet power delivery network. Okay, so this can be attributed to a couple of different things, including, do I have enough decoupling capacitors? Are they the right values for my entire frequency domain? Are they mounted well? And am I using a correct stack up in order to ensure a quiet power delivery network? So HyperLynx PI can address both the DC and the AC realm for you. And if you're not currently doing any power integrity analysis, it might be coming into play soon for you, because it is a big issue for designs with a lot of components on there, a lot of components drawing power off of your power planes at different rates. That can really cause some issues. Okay. I just wanted to address a little bit about performance. So some people do not do any simulation at all, and then others might actually just be confused as to why we don't just drop our entire board, our entire design into a 3D field solver in order to generate an extremely accurate model over your entire frequency domain that you're going to be working with. There's just a couple of issues that we want to, that would most likely not make this effective, is the time for both the setup and the simulation. If you've ever used a 3D field solver, it can be very time consuming to both set it up and simulate. Can take hours, if not days, depending on the complexity of your design. Cost, it'd be very expensive to set this up just in a time-based manner, and then as well as having a powerful enough computer to run that. And then the accuracy, we might have to actually reduce the mesh size to achieve a convergence or an actual solvable 3D field. So that's why we here at Oasis and Mentor think that it is much more efficient to use multiple tools that are targeted as well as optimized for the specific design task that you want to accomplish. So HyperLynx Family essentially can help you in all of those fields: signal integrity, power integrity, and then DRC for your EMI or EMC. And then EMI, if anyone's unfamiliar with that acronym, it is electromagnetic interference, and that can be caused by a multitude of issues, which we'll get to in just a second. So here's just a general overview of what we can do with the HyperLynx family. So HyperLynx is made up of two major components, and that is going to be line sim and the board sim tool. Okay, so line sim is kind of a what if exploration box for SI and PI issues. It allows us to essentially draw the interconnects on a whiteboard. You'll actually see line sim here where my cursor is right now. And that is just showing we have a driver, some transmission lines, maybe some vias, and then a receiver. Line sim allows us to do, to basically help develop our design constraints. We can sweep different values of the stack-up parameters, the transmission line parameters, and then play around with our different drivers and receivers if we have that type of flexibility. We can actually run simulations and see the rise and fall time, and then how they are affected on all of those different swept parameters. Okay, so with all of our line sim tools, we do have an integrated 3D full wave solver. We can actually solve for via models. If we're running above 4 gigahertz, we kind of need a more accurate via model because it can play into a major effect into our signal quality. So that 3D full wave solver is actually able to solve Maxwell's equations on a part of your interconnect or that via structure, and then we can use the model that is generated from those equations in our simulations directly within line sim. Okay, so also similar to line sim is the board sim. So line sim is kind of our pre-layout simulation tool, which helps develop design constraints. And then our board sim tool is basically our post-route verification for SI and PI issues. Okay, so how board sim can be used very effectively is it can do a batch simulation of your entire board or a subset of traces to make sure that they're not going to be over exceeding your overshoot or undershoot or any timing, crosstalk, any types of those issues. We can set it all up to do a very broad check, highlight any of our hot spots on our board, I'll call them. And then once we have those identified, we can go ahead and actually run through some more simulation manually on those critical nets that might have had an issue that HyperLynx has highlighted for us. Okay, so within the board sim environment, we're able to do our power integrity analysis as well for DC drop and the AC decoupling analysis. Okay. And then the last thing that I'll be talking about today is this HyperLynx DRC, and we'll be able to see just a small screen of that on the bottom right-hand side of my screen right now. So HyperLynx DRC is for design rule check, and it's electrical rule checking with 23 built-in rules, and most of these are in the EMI and SI space. Okay, so this is going to be basically a graphical rule checker that checks for things that can cause EMI or radiation. Okay. So this is a general design flow of how we can use our different tools within HyperLynx and in order to effectively get results as well as fix those results. So for SI, PI, and EMI, just for the stack-up design, line sim is a great tool for that. We can have a target impedance calculator built directly into that allows you to look at your stack-up, and it can bring in your stack-up from all of your designs, and then we can actually play around with that to see what if we change our stack-up, how will that affect our target impedances, and how will that essentially affect our signal integrity quality throughout the board. Okay, so this, I won't go through this in great detail, but this allows us to see where we can use our line sim tool, our board sim tool, as well as our HyperLynx DRC tool for our different steps in our design verification and problem fixing steps in our design. Okay, so just a little bit more about HyperLynx DRC, because the name does not give away too much of exactly what it does. So again, DRC stands for Design Rule Checks. And what it does is it's essentially automating our manual design check for EMI issues. Okay, so how it can typically be done is there's an EMI expert in your company that will go through layer by layer or a few layers at a time and check for common design issues that can cause EMI. Now, HyperLynx DRC allows us to do this automatically and graphically, so it can reduce days of manual design checks. It does include built-in rules. So these rules are for EMI, SI, and PI. And the reason that this is a graphical rule checker is some of you may know that it can be very difficult to actually simulate EMI. So how we have addressed that now is to actually set up just graphical rule checks that are looking for types of things in your designs after they've been routed that can cause EMI. Some small examples for that are traces crossing gaps in your reference planes that can drastically change the impedance that those traces are seeing and cause the signal to start radiating. Also, another option or example of that is metal islands. So isolated metal islands, if a signal is going high speed right next to that, it can actually be affected by the crosstalk essentially of that and become an antenna. So HyperLynx DRC will be able to check for all of these rules and more. I'll actually go through this tool as well to show what types of rules it's checking for. All of these rules allow for customization. So it allows you to actually set parameters for all of these rules it's checking and then set them as a company standard. Now that we have set that as a standard, anyone in your design team can actually go ahead and use this to check for your EMI issues early in the design. Okay, so this is just an example flow of how we can use HyperLynx in our design flow in order to screen for those SI, PI, and EMI issues. Okay, so first I'll go ahead and work in the line sim environment to develop the stack up and help develop our constraints that we're going to be using throughout our design process. Then I'll be using board sim to do a quick batch signal integrity check to highlight any spots on our board that we might need to work on a little bit further. And then we'll also use board sim to simulate voltage drop and highlight any issues that we have in our PDN. And then finally, we'll move on to DRC to check for EMI issues. Okay, so I'm not seeing any questions right now, so that's good. Again, if you do have any questions, please feel free to write those in the chat box and I can address them as we go, or maybe wait to the end if it's a little bit more relevant then. Okay, so I'm going to go ahead now and hop into the actual tool now. All right, so the beauty of HyperLynx is that it's a CAD agnostic tool, meaning that you can really bring in a design from any EDA tool, whether it's OrCAD, Altium, or Allegro, and bring it in and do your simulations in HyperLynx. Okay, so what I'll be showing today is actually utilizing DX Designer, which is Mentor Graphics schematic capture tool, as well as a PADS professional layout tool, where we can actually automatically bring in our design objects from that layout tool or the design entry tool into that simulation tool. Okay, so again, like I was saying, for the initial use of HyperLynx on line sim is the ability to help develop some design constraints. So what I can do here is I can select two nets in my design and I can right click and just hit the HyperLynx line sim. What this will allow me to do is export these two nets and the interconnects that they're seeing over into our HyperLynx tool. Okay. So what you'll see here is essentially our interconnects for these 4 different nets. Okay, just to make it a little bit easier to work with, I'm going to go ahead and delete 2 of those sets. So we're only working with 2 drivers, 2 receivers, and you'll see in the middle here, this cylinder looking thing is essentially our transmission line that these 2 nets are having in this interconnect between the driver and the receiver. Okay. The first thing that I want to highlight is the use of the Stack Up editor. So like I said, the real use for HyperLynx Line Sim before we actually do any layout and routing is to help develop our constraints and help develop our Stack Up. So you'll see here on the right-hand side, we kind of have a cross-section view of our board with all of those electrical layers and non-electrical layers in there as well. We've got a few different tabs in here to show us what types of layers we're using. We can actually set the thickness of our different copper layers in mils or ounces. And then we can go ahead and actually play around with our dielectric constants just to make sure that those are set up correctly for how you're going to be using those with your contract manufacturer. So there's a lot of different tabs in here that can help you understand the different effects of our Stack Up on our actual design. But if I want to go to a target impedance planning, what we'll actually be able to do is on a layer by layer basis. Again, we can set the thickness, the dielectric constant, and then the target impedance. And of course, thickness of copper as well as dielectric constant, that's going to affect how our impedance plays out. And then we're going to be calculating for our actual trace width that we want on that layer, okay? So how this can be useful is to help you have a base level constraint for your trace width on a layer by layer basis if you're shooting for a target impedance on that layer. So if I want to go ahead and adjust this to 125 ohms, we should, or 100 ohms, we'll actually be able to see that the trace width is decreasing, which makes sense because the impedance is going up. The trace width needs to decrease in order to meet that target impedance. Okay. Likewise, we can just play around with the actual target impedance and we'll see how that trace width is going to be affected. So this is solving for a single-ended trace. We can also solve for a differential pair where I am able to actually set the differential impedance as well as the trace width, and then it will actually give us the gap that we need in the separation gap that we need between that differential pair. Okay. So this can really help you develop those constraints for both single-ended and double-ended traces. So there's a lot of power that we can actually do here within the pre-layout environment, the line sim environment. We can actually go ahead and just run an interactive simulation. If I just click on the simulation button, what this will do is actually allow us to run a simulation on that driver and the receiver. Okay. So you'll actually see that I did a falling edge simulation here. I can also do a rising edge or an oscillation. And we'll see that if I go ahead and make this side-by-side view for us, we'll see that U2 is the driver. So both green and red are the driver. And then the pink line here is the receiver. So this makes sense. This is just essentially a digital oscilloscope for your interconnect design. Okay, so I'm going to go ahead and just turn off those two. So we'll see that we have a delay from the green to the pink. And you'll see here, actually in our HyperLynx Line Sim tool, we have a red line or a red arrow pointing at this node and a pink arrow pointing at this node. What this is showing us is that is where our probes essentially are for our digital oscilloscope. Okay. What we can do here is actually go ahead and use this tool to calculate some of our necessary calculations. So we have a negative overshoot for this signal of 549 millivolts. Okay, so that might be a little bit too much for some of our designs. So what we can play around with in the Line Sim tool is some different topology schemes. We can actually add termination schemes or we can just sweep some different parameters. So the last thing I'll show within here is the ability to sweep different parameters in our interconnect design. So opening the Sweep Manager, you'll actually see that we can sweep the stack up layers if we would like. The IC modeling, we can actually change some of the parameters that we have. Or what I'm going to do right here is actually just sweep transmission line 1, which is this transmission line here. And I'll sweep the actual length of this transmission line. So this will be how long the trace is, essentially. And I'll go from 2 to 5 inches in half-inch increments. Okay. Now, once I click on Run Sweeps, we're actually able to see all those different values for those different sweeping parameters that we did. And here I'll just zoom in a little bit further. So if I hold my mouse over one of these graph lines here, you'll actually see that we have the transmission line 1 length is 5 inches. So we'll see that the delay is getting worse and worse as we make that transmission line longer, which definitely makes sense. And it's not really affecting the undershoot, which also makes sense. So this tool allows us to essentially do what-if scenarios to see what if I change the transmission line to this, what if I add a series termination resistor, how does that affect our overshoot, how does that affect our undershoot or our timing on these signals, okay? So I see a question from Fadi, and he says, is there training for SI-PI EMI? So Mentor Graphics or Oasis doesn't really offer training just on SI fundamentals and actually the topic of SI. They do offer training on HyperLynx itself, which can help you address your SI issues, but it does not have training on just the concepts themselves, if that makes sense. Okay. All right, so going back to our PowerPoint, we've now achieved a line sim to develop stack up and constraints. That is what we've done so far. So now that we've developed our constraints and our stack up, we can forward our schematic onto the layout and they can complete the layout. Okay. So now what we'll do is we'll do a board sim to do a batch signal integrity check for our design. Okay. So again, HyperLynx is a CAD agnostic tool and we can bring in designs from any CAD tool, but just for this example, I'll show it going over from the PADS professional environment or the Expedition PCB environment. What I can do here is analysis and export it to a HyperLynx SI-PI thermal. Okay. Okay, so as you can see, it opens up the design, and this is in our board sim tool. So it definitely looks a little bit more like a board compared to the line sim tool with all of our traces, with all of our copper brought in, all of our components. Again, just to show, we do have the ability to look at our stack up again and adjust some of those parameters or again, solve for target impedance. What we also have the ability to do is do some more simulations within here. So if I go ahead and do a simulate SI, we have the same option to do a simulation just like we did in line sim on a net by net basis, okay? So if I want to select a net, I can just filter for the net that I want, this DDR DQ0. Select that and just go ahead and run a simulation directly on that net. Okay. So this gives us basically the same results or the same looking results as we did last time And if there's any issues, we can definitely go ahead and take a look at those. What we can also do, which might be a little bit more powerful in this case, if you don't know where to start on checking for SI issues, we have the ability to run a generic batch simulation. Okay. So what the batch simulation does, there's a lot of information going on in here, but I'll try and make it clear. We can run a signal integrity and crosstalk simulation on selected nets. So we can select all of the nets in the design. It might take a little bit while, but you can definitely do that, and it'll flag anything that might be out of whack. Also, we are able to do a quick analysis. Okay, so quick analysis checks for line lengths. If they're too long, then the Terminator Wizard will actually calculate the impedance based off that and say, hey, these traces might be a little bit too long. You might want to take a little bit closer look at them. The quick analysis does not require IBIS models or IC models for it to run, but the SI checks themselves actually will use models that you have assigned and actually run simulations on there. Okay, so I'll be running both a detailed simulation on a few nets and then a quick analysis on every single net in the design. Okay, so here's where we're actually going to be able to select which nets we want to check on our design. Excuse me. And just for the sake of brevity here, what I can do is select just these DQ0 through DQ3. Okay, so if I want to select just those nets, we'll check those for undershoot and overshoot as well. So again, you could select every net in the design if you wanted to, and have these base level constraints to check for. But on this particular case, I'm just going to select these 4 nets and then use a quick analysis on the rest of the nets in the design. Okay, so there's a lot of options within here, a max time limit, a monotonicity threshold that we can set as well. And then again, we can select nets for a quick analysis. This isn't going to be doing those, it's not going to be using any IC driver or receiver models. It's just basically going to look at the interconnect and gauge if it's too long or too short for your needs. Okay, so just some more simulation check boxes that we can click for IC model corners, fast, strong, typical, or slow, weak. I'm just going to go with typical, and then just model voltage references that we can select. High accuracy SI mode just allows it to do some further simulations, but it will take longer. And then it will also check for crosstalk as well. So this is where we're actually going to set default IC characteristics. Again, this is for use if you don't have any models defined already for your components. We can just assign a basic rise and fall time, output impedance, input capacitance, as well as a voltage peak to peak. Okay, so the last thing I've got to select is crosstalk simulation. Again, this can highlight any areas on the board where you might have too much crosstalk. And then the last thing I think we're going to check is loss for your actual frequency dependent loss on your interconnects, and then your via modeling on your traces. Okay, so what we have the ability to do is create an HTML report and a summary file as well. I'm just going to go ahead and click next. And now it's going to start simulating. It's going to be running those signal integrity analysis, actual simulations on those 4 nets that we chose. And then it's also going to be doing the quick analysis on every net in the design, showing if there's any traces that might be too long or any crosstalk issues. Okay. So here is our HyperLynx batch mode report. This is the HTML report that was generated off of our quick analysis that we just did. So you'll see these are our quick analysis nets that we just had selected, and you'll see that most of them are no violation, okay? But some of them there at the top that we just looked at, we'll see net too long in this fail category. So if I click on those, these are all clickable links that allow us to actually go ahead, and it says net too long. The found length was just under an inch, and the maximum recommended length that HyperLynx calculated is 0.928 inches. So it's just a little bit over that. So you might have the engineering intuition to say that shouldn't be an issue, or we can use this report to go ahead and delve down a little bit further into this and do some further simulations. Okay, so this is all the quick analysis that we just did. And then also we have a detailed signal integrity and crosstalk section that we can take a look at. So here you'll see that we have those DDR-DQ nets, and only 4 of those nets that we had. So you'll see that we have about half of them passing in all categories, and then about half of them also failing in our overshoot. Okay, so especially on your DDR nets, this could be a major concern. So this is a really easy way to go ahead and check all of these nets at once to see our overshoot and undershoot. So if I click on that overshoot, we'll see the overshoot table here that's showing DDR-DQ2 had an SI overshoot of 650 millivolts, where our requirement was 600 millivolts. Okay, so you'll see most of them are right around 600, some of them a little bit over, some a little bit under, and we might need to take a look at that a little bit further. Okay, so for this DDR-DQ2, now that we've found an issue using HyperLynx BoardSim, what we can do with DDR-DQ2 is first I'll select this. And we can do a lot of information now with this net that we've highlighted that might have an issue. Again, we can just run a rising edge simulation on there to go ahead and actually check our overshoot. And it's showing that we've got 624.2 millivolts of overshoot. Okay, so now that we have this issue, how do we go about figuring out how to solve it in our actual design? HyperLynx allows us to select this net, and what I can do here is export the net to the free-form schematic. What this will do is export it back into our line sim view with all of our interconnect data, including the transmission line, as well as any vias that we have associated with it. Okay, so here's this DDR-DQ2 net, and we know that we have an issue with it. Here is where we can play around with possible solutions. For example, we can change this transmission line from the stack up from a different layer to, so currently it is on layer 8. We'll see it's on layer 8. If I change that to layer 10, for example, how does that affect our results? Okay. Again, within here, we can run all of the sweep manager that we had before. We can sweep the stack up again. We can sweep all of these transmission lines, TL1, TL2, and TL3 for different values, and really see how we can fix our signal integrity issues. Okay. So that is kind of a quick example of how we can use HyperLynx BoardSim to highlight design issues that we have with our nets, and then also use it to help us understand how to fix those issues. Okay. All right, so going back into our example flow, we've gone ahead and used line sim to develop our constraints and the stack up. We've also gone ahead and used board sim to do a batch SI check and narrow down some of our issues to see how we can fix those. Now we'll use board sim to simulate voltage drop. So using the same environment that I'm currently in, I can now also simulate the voltage drop for some of our power planes. So if I go to simulate PI, you'll see we have run DC drop simulation. What this allows me to do is actually go ahead and take a look at all of our different nets or power planes that we have defined in this design. So you'll see this is 3.3 volt. We've got a lot of different power planes defined on this board. Okay, what I'm going to go ahead and take a look is our 1.8 volt source. And you'll see this is kind of what it looks like in our design currently. So the first thing that we have to do is assign models. So if I click on the Assign Models dialog, we'll see all of our different pins and components that are connected to this net. Okay, so these, for example, CR1 is the reference designator, and pin 2 is connected to this net. Okay, so pin 2 is connected to 1.8 volts. And we'll see, you can also assign a reference model, such as ground, or reference net. Now for the models, in this example, all we have is a DC sync model. So what this is showing is that CR1 pin 2 is drawing 500 milliamps with, I believe that's 100K ohm resistance for it. So what I can do here, just to look at that a little bit further, is if I click on Assign the DC sync model, this is how much current this particular pin is syncing off of our 1.8 volt source, or 1.8 volt voltage point. Okay. We also have, so here we've got J8, J9, and J13. We have these assigned as our voltage model. We can define these as a 1.8 volt, resistance of 1 milliohm, and an inductance of 30 microhenries. Okay. So this is how we set up our design to be simulated for a DC drop simulation. You'll see that we have quite a few pins connected on here and syncing quite a bit of current. So we'll see how much voltage drop we're getting from this. All right, so what we have the ability to do is set some constraints down here in the bottom left, such as maximum voltage drop on any point in this plane is 50 millivolts, and as well as maximum current density and via current. Okay. What I want to do here is to create a report from our results in an HTML format. Just gives us a little bit easier view to see kind of our results. So I'll go ahead and click Simulate, and this will just run our simulations very quickly. And this is going to open up quite a few things. This is our HTML report that we'll talk about in just a second. So what it first gives us is a cross-probable view of all of our different pins on the design. So this is showing us our location of the pins, the layer that it's on, the current, and the voltage exactly at that pin. So if I click on any of those, it's going to highlight that via in this layer and show us exactly where it is. So this just gives us a really quick check to see if there's too much current being synced by some of these pins, or if the voltage drop is too great at some of these areas too. A very easy to understand view is the 3D view of our voltage plane. Okay, so this is kind of a 3D view of that power plane. Why it's 3D is because it's showing the higher layers or the higher level sections is going to be higher in voltage. So if I hold the control key at this top point, you'll see that's 1.8 volts. So that's got to be right next to that power pin essentially. Now if I move this around, you'll see that there's not too much voltage drop going on. We're still only at 1.799 volts right now. But as soon as I start going down through the neck down areas, you'll see the voltage is going to actually start decreasing. Okay, so there's not too much voltage drop in this particular power plane, so that's probably a fairly good design right here. But you'll see down here at this red section, we've got 1.795, still only 5 millivolts of voltage drop, so nothing to be too concerned about. Okay, what we can also do is set a threshold. So a threshold will be showing exactly where this plane is less than that threshold that we just set. So you'll see we've got a gray, icon or a gray cross section showing us that everything below this gray area is going to be below our threshold that we just set. So that is voltage drop in this window. What we can also do is go to a 2D view, and if I want to go ahead and look at the DC current density, I can set it to that. So again, just like the voltage drop, I can go ahead and hold control, and it will show us the current density at that particular point in time. So 8.7 milliamps per square mil. Not too much. I'm not really sure. I cannot remember what we set for our maximum constraint there. But again, this is going to be into effect due to the amount of copper there, how many vias are going through that section of copper, and which layer it's running on. Okay, so this can really help you quickly identify any of your PI issues, either in current density or in DC drop. Okay. And then also looking at that HTML report very quickly, we'll see that the max voltage drop was 5.2 millivolts and our threshold was 50 millivolts. So we're definitely under that. I think this is a pretty good design for this 1.8 volt source. You'll see maximum current density, we got 28.11 milliamps, and I believe we set 25 milliamps right there. So just a little bit above that. Okay. And then if I click on the net, it actually gives us the pin at that location and then the current that is either being sourced or taken away from that power plane. Okay. So going back to our flow again one more time, I know that we're running close to an hour, so I'll make this last part a little bit brief. Is to check for DRC issues that might cause EMI. Okay, and again, I'll be running this through the PADS professional layout space. What I can do here is go analysis, export to HyperLynx DRC. Again, HyperLynx DRC is a graphical rule checker to check for issues that might cause EMI in your design. Okay, so this will open up our design actually in our HyperLynx DRC tool. So what this is doing is going to be able to run rules on all of our nets or just a subset of nets in our design. Okay, so here it actually will allow us to see the different rules that we are going to be able to run. So for example, we've got edge shield, filter placement, IO coupling, nets crossing gap, return path, all of these different rules. And you do not have to run all of them, and you do not have to run any rules on your entire design. You can set up custom groups that, for example, I only want to run these rules on my DDR nets. We can set that up so it works that way. Okay, so just to take a look at what this looks like, if I select nets crossing gap or any of these other rules, it gives us a brief overview showing what this rule is actually doing. It's checking that the signal traces have a solid reference plane beneath them, which again can be very important for not causing radiation issues. So how we can set these different parameters, you'll see here, is these are all customizable. We can set all of these different parameters to what you think is good for a company and set it as a company standard. That way anyone can run these rules on their designs. Okay, so obstacle length, for example, in a kind of a cutout in the plane, we can set that as a 300 mil diagonal. Also, we can set for stitching vias. So we've got a stitching via selection between those two planes. If it's within 300 mils, this won't be flagged as an error. Okay, so this does a really good job of going ahead and explaining to you what these different rules are checking for in this tool. Okay, so for example, I/O coupling, if we've got a high-speed net and just an I/O net, we need a minimum separation between those two just to make sure we don't have any unwanted I/O coupling. Okay. So for example here, just to show you how one of these are ran, if I go ahead and right-click execute, actually I'll go ahead and do nets crossing gaps. I'll just go ahead and right-click execute on that. And it'll go ahead and start thinking. And it's found 264 violations. Okay. So if I go to the violations window, we'll actually be able to see all of our violations that we have in this check. So what I can do here is I'll just click on this net and it'll highlight exactly where it is in our design. Okay, so the details on the bottom right-hand side of our screen now shows us what that net name was, what layer it is actually being routed on, and then the reference plane. So you'll see it's crossing this gap right over this reference plane on layer 7, and it shows us the actual gap width. Okay, so how this can be used is it can check for these types of issues, and then you can go back to your layout and adjust that accordingly. Maybe add a stitching via here or route it in a different manner. Okay, so that's just some ways to address these types of issues. Some other rules that we're able to run is impedance. So there's, first we have EMI rules, PI rules, and then SI rules as well. So a very powerful SI rule that we can run on is, for example, differential impedance. And this will actually give us a little bit, again, of an overview of what it's checking for. It's checking in deviations for differential impedance. For example, you'll see in this kind of picture here, it shows that it's green for all of the impedance through this section. And then as soon as we get a separation gap larger than what we had defined in our design constraints, I'm sure, that's where the differential impedance is going to be highlighted. And it will highlight that in our design in HyperLynx DRC. Okay. All right, so what we've done with HyperLynx today is gone basically through the full flow. We've gone ahead and before we did any layout, we looked at stack up and developing constraints and how that's going to affect our routability of the board. Then once the entire board has been made, we use BoardSim to do a batch signal integrity check and delve down a little bit further into those. Then we use BoardSim to just look at some voltage drop issues that we might experience. And then finally, we use HyperLynx DRC to check for any EMI issues. All right, so I do see one question from Naru, and he said, how do we decide the inductance values? And I believe you're talking about for the DC drop components. And that's basically going to come from the datasheet of our voltage regulator model. So if you're using just a linear regulator, you can probably find the output inductance on the data sheet from the vendor there, and that's probably going to be the best to use. Okay, I don't see any other questions right now. If you do have any questions, please feel free to type those in. Otherwise, here's my contact information once again, and this was recorded, and we will send out an email showing where this is hosted on our website and on YouTube. So if you want to watch it again, please feel free. Again, here's my contact information. If you have any other questions or need any other info on anything Mentor Graphics related, please feel free to give me a call or shoot me an email. Okay. All right. Well, with that, I hope this was somewhat beneficial for you guys, and I hope it was informative, and thanks again for attending. All right, have a good day. Bye-bye.